Our next presentation is by Shen, who will talk about a globally distributed and scalable data path processing framework for WALLABY science.
Hey everyone, my name's Austin and thanks for coming to my talk. I'm going to be sharing the work that I've done on a new data post-processing framework for the WALLABY science team, which is done as part of the Australian SKA Regional Centre Design Study. So first, what's the motivation for this work? Well, the AusSRC has access to the two SKA precursor telescopes, and we work with the science teams to develop an understanding for how these SRCs might be able to operate. The diagram on the right shows how we're involved in this process. So data comes from the instruments and undergoes science data processing, which is still on the telescope side, and then it comes to the SKA regional centres before being disseminated to users. And for this design study, the users are the scientists involved with the surveys on the left. So we have Possum, Emu, Flash, EOR, and WALLABY. And I've been working with WALLABY over the last few months, so the rest of the talk is focused on their post-processing requirements. To give you an overview of WALLABY, it's a ASKAP neutral hydrogen all-sky survey, and it's very exciting because it provides a map of neutral hydrogen that's significantly better than what was available previously with HiPass. So it has much better spatial and spectral resolution and greater sensitivity, and yeah, we're expecting to detect 500,000 galaxies and process data on the order of 6 petabytes by the time the full survey is complete. So yeah, it's a new big data problem, and currently we're in the pilot phase, and we are working with WALLABY in this pilot phase to develop a post-processing framework. So this flowchart summarizes the activities involved in WALLABY's data post-processing at the moment, and this takes data from the telescope and generates the advanced data products, which are tables that scientists can interact with of the sources in that patch of sky. So the first step is data retrieval, where data is copied from CASDA, which is the telescope archive, into our computing resource. Then we do mosaicking, where two footprints, which are slightly offset images, are mosaiced together to generate a higher signal-to-noise image that is ready for source finding. The source finding has two steps. First is the execution of an automated source finding application, which will generate a bunch of detections with properties. And then there's a manual step involved where a project scientist will look through those sources and verify which ones are real and keep the real ones for the final catalog. And then at this point, the data is either shared to the users, or we have collaborating institutions that will use this source data to generate advanced data products, so kinematic properties by the Canadian Institute, CIRADA, and multi-wavelength properties by the Spanish SKA Regional Centre. And as the AusSRC, we focus on the stuff above the arrow, so data retrieval, mosaicking, source finding, and then user access. I'll go through different parts of this framework, and I'll start with the computing pipelines. So we use a tool called Nextflow to compose pipelines which capture the steps that I mentioned previously. And you can see that in this diagram here. The pipeline at the bottom there has 3 steps that you saw before, and yeah, they run on a high performance computing resource, Slurm cluster. And yeah, one of the good things about Nextflow is that you can take a pipeline that's composed and run it on any cluster of that nature. So you can run it on any Slurm cluster or other HPC clouds that are available in like Google or AWS or whatever. And the way that these pipelines are composed is really nice. So you can see a little code snippet which shows you how the main pipeline is structured. We have a download, mosaicking and source finding like component, and the main pipeline just takes in some SBIDs, which are identifiers for the footprints that you want to process, and then you just execute these 3 different components, and the output will be the data that you want to generate. So that's a quick overview of the highest level of this pipeline, but I'll go into the components in a little bit more detail. So I'll focus on the source finding component, which is quite interesting. You can see in the code snippet on the left how this source finding workflow component is structured. So there's a collection of configuration steps, followed by the execution of the source finding application, Sophia, and then Sophia X, which is used to take the output of Sophia and put it into a database. And yeah, on the right, you can see how each of the processes are defined. So we have some container, which determines the execution environment. And yeah, each of these processes runs inside a container. And the script that you want to execute is really straightforward. You just run the pre-installed application, Sophia, with the parameter file. You can see at the top there. And yeah, it's as if you were running this on your local machine. So yeah, it's a really nice way of composing different processes that have different dependencies, and you don't need to worry about any of the dependencies because you're using containers. So I want to go further into one of the processes. So I want to talk about the source finding application. What I want to illustrate here is that the application for doing the source finding is something that has been contributed to us by the scientists, and we just use their code as part of this pipeline that does a bunch of the different computing steps required for their workflow. So Sophia 2 has been developed by members of the WALLABY team, and all we've had to do in order to run it is containerize it and then put it in our Nextflow pipeline. So it's a really nice way of taking code from scientists and letting them use whatever tools they wish and running them on our system in this nice way. So that was the computing part. Now we've got the database and access to that, which is quite important in this workflow. So we have a Postgres database that stores all of the detection information and the source information, and then both the community and the project team will have access to that. So as I mentioned previously, the project team will have to manually inspect the output of the source finder to verify that the source is real, and you can see the schema on the left. So you have the detection table with all of the properties and products from the source finding application, and then you have a source table with just a name, and that name is the name determined for that source by a scientist once they've decided that it is a real source. And the project team will write to that source table through a Jupyter Lab interface, which runs on top of Open on Demand. So that Open on Demand provides the view into the cluster, a graphical view, and we use Django for the object relational mapper that allows these users to interact with this database in Python and using Python objects. And yeah, the same interface is provided to the community as well, except they have read-only access rather than read-write. And yeah, this means they can use these notebooks to either download the data to run on their local machines, or as the notebooks can be used as a place to do their own custom analysis. They can also use IVOA to use tools that they're familiar with, like Topcat. So yeah, there's a bunch of interfaces that we provide to access the data. And I also wanted to mention that the generation of advanced data products is a collaborative effort between the AusSRC and Cerrado in the Spanish SKA Regional Center, which I mentioned previously. So we're also developing this network of replicated databases where different tables are shared between us depending on the data that we're generating. And Manu from the Spanish SK Regional Center has a poster on how we're making use of Bucardo to do this, so go check that out if you have the time. Yeah, and that covers each of the different parts of our processing framework. So hopefully you can see that we have this computing part, which is what does the bulk of the data post-processing, and then a platform part which facilitates this processing and allows us to execute these pipelines and provide interfaces for the scientists to interact with their data or to share the data across other regional centers. So the diagram on the right covers the technologies that we use. We are lucky enough to have access to an OpenStack cloud allocation from the Pawsey Supercomputing Center. This gives us lots of flexibility to play with the tools that we want. Yeah, we've installed a Slurm on that and BGFS for a POSIX file system. And yeah, on that Slurm cluster we use Nextflow for these pipelines and Singularity and Docker for containerizing the applications that we run in those pipelines. And we also have Jupyter Hub that allows for the manual interaction of data. We have a few interfaces, so Open on Demand gives the users a graphical view into the system. And yeah, we also have IVOA for access via popular tools in astronomy, and then Django for interacting with the database, which is a Postgres database, and we have Bucardo for replication. So the technology stacks that are required for different types of users are completely separate, so scientists can use whatever tools they want for writing their code. Developers of pipelines in this system just need to understand how to use Nextflow and to containerize applications, and then your system administrators have to understand how to maintain the Django ORM or interact with SQL to maintain the database. And yeah, this framework is being used for the pilot phase 2, and we're using this phase to test out the system and make sure there are no more bugs before it moves into a production setting. And yeah, from there we intend to automate the operating of this pipeline, so the execution could be automatic instead of manual. We want to provide an interface to look at the progress of the survey, so see what data is available in the archive, see what's processed, and look at that visually. And all of this is being contributed to a more generic cloud platform for processing of astronomy data, which we call the Radio Astronomy Data Enhancement Cloud, and that's something we're working towards, and the pipeline that we've developed will contribute to. So yeah, thanks for listening to the talk. If there are any other questions, feel free to message or send me an email.
Thank you very much indeed.
Oh.
I see no questions on Discord. Are there any questions in this room? I see none, so if there are any follow-up questions, please do use Discord to ask them or send an email. Let's thank the speaker again.